All right, hello and welcome back. In this video, we are going to be looking at free body diagrams that involve components. And what I mean by that is this is a force that is being applied horizontally, and we can draw that on our free body diagram. But this force is being applied at an upward angle, and this is going to involve components. And this force is being applied at a downward angle, and it also is going to involve components. So let's look at three quick examples, and then we're going to come back up here and kind of write our summary statements. So I'm going to start down here with a physics student pushes a 135 kilogram refrigerator across the floor by applying a 600 Newton force horizontally. If the coefficient of friction acting between the floor and the refrigerator is 0.4, calculate the acceleration of the refrigerator. All right, so I'm going to start by drawing a picture, a free body diagram of the refrigerator. So I can see that it's sitting on a flat surface. So I kind of do my floor. This rectangle will stand for the refrigerator. And then I turn the object, the refrigerator, into what's called a point mass, or into a dot. So I'll put the dot there. That dot then is going to be the origin of my XY grid. So I'm going to kind of sketch a little XY grid on here. All right, in this problem, we are pushing the refrigerator with a horizontal force. So coming off my point mass, which stands for the refrigerator, is going to be that horizontal force, and I'm going to label that as an applied force of 600 newtons. So the refrigerator also has a gravitational force, or a weight, and the weight is equal to mg, and the mass is 135 times 9.8, so that is 1323 newtons. So the refrigerator pushes onto the floor with a force of 1323 newtons, which means the floor pushes back with the normal force of 1323 newtons. All right, then we have friction in our story, and I'm going to make my friction arrow a little bit shorter there. So friction is mu times Fn, so that's 0.4 times 1323. And that equals 529.2 newtons. All right, so I have my classic free body diagram, and then I can calculate the acceleration of the refrigerator. And I know the refrigerator is accelerating because my Fa is bigger than my frictional force. So the net force is going to be the difference between the two. And then I can solve for the acceleration. So let's finish this one. And I already number crunched everything just to go a little bit faster here, and I get 0.25 meters per second squared. So when this student applies the force and pushes on the refrigerator, it's going to have an initial acceleration of 0.52 meters per second squared. It doesn't necessarily mean that he continues with that force as he pushes it across the floor. So this should have had no surprises in this free body diagram. So when you push horizontally, we notice that Fn does equal Fw. But the point of this lesson is when I pull at an upward angle or push at a downward angle, Fn does not equal Fw. And that's the main point that we are going to be looking at. So we have two examples of that in the back. So the first one is somebody pulling with an upward angle. So let's quickly read the problem first. A physics gal pulls a 15 kilogram sled by pulling upward on a rope with a force of 140 newtons. The rope makes a 35-degree angle with the horizontal. If the coefficient of friction acting between the sled and the snow is 0.25, calculate the acceleration of the sled. So this time, I'm going to draw a rectangle that stands for the sled, and then I'm going to turn it into a point mass. So I'm turning the sled into a point mass, and I'm going to sketch my XY grid again, just so I have it ready to go. All right, but this time she is pulling at an upward angle like this. So I'm going to label that upward angle as an applied force of 140 newtons. And it says that the rope that is coming off of the sled, which is the point mass, is 35 degrees. So what that does is, because I have a force acting at an angle, I have to break that force down so that I know what's happening in the x direction. We'll call it the x component of the force. And what is happening in the y direction, we'll call that the y component of the force. All right, to figure that out, I basically just made a triangle, and I'm going to use right triangle trig to calculate the x and the y components. So let's start with the x. I notice that it is adjacent to that angle, so I'm going to write cosine of that angle would be the adjacent over the hypotenuse. So the x component is going to turn out to be 140 cosine of 35. And if I number crunch that, I get 114.68 newtons. The y component, I notice, is opposite the 35, so I'm going to write sine of 35 is going to be the y component over the hypotenuse. So this is going to turn out to be 140 times sine of 35. And if I number crunch that, I get 80.3 newtons. Now let's pause for a minute and talk about what that means. So when I pull something at an upward angle, part of my pulling propels the sled in the x direction, 114.68 newtons. But I also am creating an upward force of 80.3 newtons at the same time. Now, I'm not saying that the corner of the sled is being lifted off the ground, but I am saying that there is an upward force acting on the sled. So let's continue with that, because we know there's also a downward force acting on the sled, and that would be the gravitational force or the weight. So let's put that down. So we have 15 times 9.8, and that's 147 newtons. All right, so now I want to talk about the normal force. So the normal force is the force that a surface presses back up. But look what's pressing onto the surface. You have a force of 147 newtons pressing down, but you have a force of 80.3 newtons that is pressing up, or that is pulling upward because of you pulling that rope at an angle. So the normal force is going to be, I have the force pressing down minus the force that's going up. And so if I subtract that, I have 147 going down and 80.3 going up. That adds up to, or subtracts to 66.7 newtons. That means that only 66.7 newtons is pushing into the ground. And so the ground is going to push back, Fn pushing back, with 66.7 newtons. That's a little bit tricky. All right, we still have friction in our story. And so I'm going to go over here and calculate the frictional force. and that's going to be mu times Fn. So that's 0.25 times our 66.7, and that's equal to 16.68. So our frictional force, if this arrow stands for 114, 16 is going to be kind of tiny, so I'm going to draw it like that. And then I'll label that in my picture. All right, so we have everything in our free body diagram. So now we can calculate the acceleration of the sled. And we can do that by looking at the net force that's happening, because that causes the acceleration. So we have a net force of 114 in the x direction, and working against me is 16.68. So I'm going to take the x direction minus the friction. And I'm picking the x direction because the sled is sliding over the snow in the x direction. And then I'm just going to solve for the acceleration. I'm getting the mass from here. And so when this gal first pulls on the sled with this force, she's going to get an initial acceleration of 6.53 meters per second squared. All right, so let's put that back. Well, let's do that in a second. We'll do that in a second. Sorry about that. All right, let's look at the last problem, or the last example. So this time we have somebody who is mowing their lawn. A physics chap mows the lawn by pushing down on the handle of a 12-kilogram mower with a force of 150 newtons. The handle makes an angle of 40 degrees with the horizontal. If the coefficient of friction acting between the mower and the grass is 0.36, calculate the acceleration of the mower. All right, so this time I have a lawnmower. Then I'm going to turn into a dot, into a point mass. And that point mass, the lawnmower now, becomes the origin of my XY grid. All right, so this one's a little tricky because he is pushing down on the handle. So this arrow that I'm drawing really should not be part of my picture, but let me just show you what's happening. So he's pushing down like this. And this is a 40-degree angle. So this is like pushing down on the handle. So when you draw the free body diagram, you are pushing down on the lawnmower, which is the dot. So we're pushing down like this. So this is how I draw that downward arrow. So I'm going to call that the applied force, and he's applying a force of 150 newtons. And using a little bit of geometry, alternate interior angles. So this here is also 40 degrees. So that means that we also have components acting in this situation. So part of his pushing down is going to propel the lawnmower in the X direction. And part of it is going to create a downward force on the lawnmower, kind of like pushing it into the ground. So we can do our trig again, just like we did back up here. But we can kind of jump to the punchline that the x component will always turn out to be the hypotenuse times cosine of 40. And the y component will always turn out to be the hypotenuse times sine of 40, as long as I'm using an angle with respect to the x-axis. All right, so we'll number crunch each of those, and I get 114.91 newtons, and I get 96.42 newtons. All right, so what else is going on? So we have, the lawnmower has FW. So let's calculate the gravitational force, or the weight. So that is going to be 12 times 9.8, or 117.6 newtons. All right, let's talk about Fn. Fn is the force that a surface presses back up. So what's pressing into the surface? We have Fw pressing into the surface, and we also have this y component pressing into the surface. So Fn in this situation is we have two things that are pressing down. So I'm going to add them together, and then that's what the surface is going to press back. So I have 117.6 plus 96.42, and that adds up to 214.02. So if this is 117, this is going to be a pretty long arrow there. So Fn is 214.02. All right, and I also have friction in my story. So let's go over here and calculate the frictional force that's present. So the coefficient of friction is 0.36. We just found the normal force of 214.02. So the friction is 77.05 newtons. All right, how long of an arrow should I draw? So this X arrow, this is 114, so 77 should be shorter. So I'll draw that a little bit shorter, and I'll label that friction 77.05. All right, so I have my free body diagram finished with the components, and I can now calculate the acceleration of the mower. I know it's accelerating because I have a bigger force in the x direction, positive x direction, than I have in the negative x direction. So I'm going to take the x component and subtract off the friction that's working against me, and then I can calculate the acceleration. And when I number crunch that, I get 3.16 meters per second squared. So that means when the person first pushes on the handle with a force of 150 newtons, he gets an initial acceleration of 3.16 meters per second squared. And we don't know if he continues mowing the lawn by applying a net force and accelerating across the lawn, or if he may change his force and then start to maybe mow the lawn at constant speed. All right, so let's go back and do the summary statements then. So what I wanted you to see is that when you have an object and you push on it horizontally, then we would have an Fn that equals Fw. To be totally honest, even if I didn't push on the object, even if it was at rest, Fn would equal Fw. But when I have an object, such as the sled, that I turn into a dot, and I pull at an upward angle, I end up having Fw pointing down, and then I have this y component pointing up. And because of that, the normal force ends up equaling what's going down minus what's going up. And then that would be the net force pressing down on the ground, and then the normal force would be equal to that net force pointing back up. If I have something like a lawnmower and I'm pressing down at an angle, I end up having an Fw pressing down and an Fy pressing down. So because I have two things pressing down, I'm going to add them, and then the normal force would be equal to that sum, and that would be what is pressing back up. All right, other examples that might be like pulling a sled, could be like pulling a box at an upward angle, pulling a crate, maybe pulling a wagon, if we kind of ignore the rolling of the wheels. A lawnmower, other examples might be like pushing a shopping cart, pushing a baby stroller. So there's other examples of each of these. I just use the sled and the lawnmower as my classic examples. All right, I hope this helps, and we will see you next time.